students, welcome back to the channel, and today we are going to solve a few problems which were asked in GATE 2020. So without much ado, let's get started. So the first problem goes like this. We have a beam of negligible mass hinged at support point P and has a roller support Q as shown over here. A point load of 1200 Newton is applied at point R. They are asking what is the magnitude of the reaction force at support Q. So they are asking us what is a kind of reaction force that will be exerted at this point. So it's a roller support, so the only reaction it can provide is the one which is normal to the surface. So what the roller support do is it will prevent the motion in this direction. If I use a coordinate system for the sake of explanation, let's say this is my x direction, this is my y direction, then this roller support will prevent the motion in the x direction, which in turn means that this will provide a force normal like this. It will provide a force normal to the surface, to this surface, so it will be acting like this. So they are asking us what will be that but force that will if we call that RQ, they are asking us what is that reaction force RQ. To find that, the best method is to compute the moments about this point capital P, because why this is the best point, because we have two reaction forces here, because this is a hinge support hinged at support P, so there will be a reaction force in this direction, in the y direction as well as in the x direction. So if we take moment about the point P, we can get rid of these two reaction forces. So once we do that, so I will explain it here itself. So this particular force component 1200 times 5 meter will cause a moment in this direction. It will cause a moment in the clockwise direction. Now what does RQ do? RQ times this distance, which is 4 meter, it will cause a moment in the counterclockwise direction. Makes sense? So for the system to be in equilibrium, or to be more precise, for this structure or for this beam to be in equilibrium, the moment should cancel each other, or in other words, RQ should be equal to 1500 Newton. Makes sense? A fairly easy question. Now, so the only takeaway from this kind of problems is understand the kind of support, understand the kind of reactions what a particular support will provide, then take the moments about the appropriate point. Let's move together to the next question. So here we have a circular disc of radius little r as shown over here. It is confined to roll without slipping. Very important. When you read questions from dynamics or mechanics, please try to give a lot of importance to this kind of words or this kind of assumptions. It rolls without slipping at P and Q as shown in the figure. So what is the implication when they say it rolls without slipping? It's fairly simple. So if I zoom in here at this location, there are 2 points, right? There is a point that corresponds to the plate, and then there is a point corresponding to the disc. So let's say I will call it P1 and I will call the point on the disc P2. So they are coincident points. They occupy the same position, but they are two different points. When we say that it is confined to roll without slipping, what that implies, the velocity of these 2 points, the P1 which is a part of the plate and the point P2 which is a part of the disc are the same. So velocity of both these particles are the same, or since this is moving with the velocity of little v to the left side, this point P2 also will move towards the left with a velocity of little v. Now extending the same kind of argument to this position, we can say the point Q will be moving towards the right with a velocity of 2 times v, when this is moving with a velocity of v. This is slightly counterintuitive because you will be thinking, hey, I know pure rotation of a disk when we encounter things like this. Sorry, for my poor sketch, but if I have, let's say I have a circular disk and it is rotating in this direction, then we know if it is rotating at a velocity of angular velocity of omega, and let's say the radius of the disk is little r, then we know this point will move towards the left with a velocity of r omega. I'm talking about only the magnitude here. I'm not going into the vector representation of that. It's good to know all those things. Then this point also will move to the right, but with the same amount or same velocity. Make sense? So this situation is different. This situation and this situation are different. Why? Because here we are talking about pure rotation about a fixed axis. I have my disk axis going through the center, and the disk axis is fixed like this, and it is undergoing pure rotation. But in this case, that's not the case. It is undergoing a combined motion where there is rotation as well as translation. So the best way to solve this kind of problems is by invoking the concept of instantaneous center. So this concept of instantaneous center is not very difficult to understand. So you take the snapshot of a moving object at an instant or at a particular instant of time, then you can say it's undergoing combined motion. It is undergoing pure translation plus pure rotation. It is undergoing some kind of a combined motion. One good example for combined motion is a disk rolling over an inclined plane. So as you can see, as the disk comes down, it is undergoing translation at the same time it is rolling also. So that is what combined motion means. This situation is also something similar. But to tackle this kind of problems, we can use instantaneous center. So I was explaining you the concept of instantaneous center is that for that instant you can assume or you can consider the body undergoing pure rotation about the instantaneous center. So it's just a tool to make your problems, or to just a tool to convert a combined motion problem to a pure rotation problem. Makes sense? So in that way it is very handy, because combined motion you have to use a lot of equations. But when you reduce, or when you go from a combined motion problem to a pure rotation problem, your equation gets far more easy, because as shown over here the equations are fairly easy. If you know the axis, the velocity at any point that arises out of pure rotation can be evaluated as omega times the distance. So if I am interested in to calculate the velocity of this point, let's say I am interested in calculating the velocity of this point, then let's say this is at r1 distance from the center, then the velocity is omega times r1. So it is fairly easy. So that's the motivation why we find instantaneous centers. Make sense? I think that is enough for the motivation or the importance of instantaneous center. So here I'm trying to find the instantaneous center of this system. I have only a few little information. I know that this is the velocity at this point, and I know this is the velocity of this point C. I know the velocity of point A. I know the velocity of point C as well. So now I need to find instantaneous center. From pure rotation, you know that this for pure rotation, your instantaneous center is always at the center. I'm talking about the disk undergoing pure rotation. This is undergoing pure rotation. Okay. Then this point will have a velocity towards this direction, and this point will have a velocity in this direction, and this point will have a velocity in this direction. Now you can see all the time this instantaneous center or the center of rotation falls on a line normal to the velocity vector, isn't it? I have a velocity vector like this, let's say for this point, then I draw a normal to this velocity vector. Again I can see my instantaneous center falling over that line. Make sense? So exploiting that concept, I draw two normals like this. Sorry, I draw one normal connecting these 2 points. So instantaneous center should lie somewhere here. Then I am picking that, let's say my instantaneous center, I'm assuming my instantaneous center is at point B. It is not at the center, okay? That's why it's clear from the figure also, I guess. This is not at the center, this is some random point where I call that point B. If this is the instantaneous center, then the velocity corresponding to point A will be, if I assume that this is rotating with an angular velocity omega. A body can have only one angular velocity. It cannot have multiple angular velocities, okay? So let's say if the body is rotating with an angular velocity of omega, then the velocity of this point can be written as AB times omega. Because for the time being the body is undergoing pure rotation. For the time being, for the current instant, this body is undergoing pure rotation about this point. So the velocity of point A can be written like this. I will write velocity of point A is AB times omega. Similarly, extending the same argument, velocity of the point C can be written as, again we know it is undergoing pure rotation about this point B. So velocity of point C can be written as BC times omega. We know VA is only V, then VC is 2V. So now we have a ratio for AB divided by BC. When we divide this equation, if I call that equation 1 and this is equation 2, then if I divide my equation 1 with equation 2, then I will get a ratio of AB by BC, which tells you, this is 1 by 2, AB by 1 by 2. Now I can exploit another fact that when I add these two things, when I add AB plus BC, I should get 2R. So you have two equations, AB plus BC is 2R. You know your AB is just half BC, so you get 2R. That means 3 by 2 BC is 2R. So you are asked to find the omega. Once you do your math properly, you will get your omega to be 3 by 2 times V by R. So this is how you solve this problem using the concept of instantaneous center. So the concept of instantaneous center is really handy. It is very useful when you solve vibration problems also. So thanks for watching.